Hey, what's up, guys? Chung here again. So today I want to talk about this LeetCode problem, number 1223, dice roll simulation. It's a medium problem, but to me it's like more like a medium to between medium and hard problem. I like it anyway. So let's take a look what this problem is saying here. So a die simulator generates a random number from 1 to 6 for each row. You introduce a constraint to generator such that it cannot roll the number I more than max row max I one index consecutive times. And given like an array of integers, row max and the integer n, return the number of the distinct sequences that can be obtained with exact n rows. Okay, so you have a dice, right? You have a dice, it has like 1 to 6 random numbers each time when you roll it. And the n means that you can roll this many times. And it asks you to get all the possible results you can get. But there's like one restriction here. You can only say, for example, this one here. So the number of the row max represents for this number, what's the most consecutive times you can roll this number? For example, this one. So one means you can only roll number one at most one consecutive times. For number two, same thing. You can only roll number two one consecutive times. For number three, you can roll number three two consecutive times, which means you can have like a three and a three. But the next one, if you have another, but you cannot roll another three after two threes here. Okay, and same thing for the four, five, and six. Okay. Mm, so this so this problem is a very typical or a classic DP problem. You know, it's very similar to some other problems that if you guys remember. So like for example, I think maybe you guys have remember there was like similar problem. You can paint a house with different colors of paint. You can, right? And for each of the paint you can for each time you can paint but uh you cannot paint the house. Uh, so I think that problem is like this. So you have n houses, and you have like you have different like let's say you have n houses and you have m color of paints, and for each of the paints there's like a value, right? And then but you cannot paint two consecutive houses with the same color. It asks you to find maybe to find all the possible ways of painting all the houses or something like that. Okay, so for that problem, I think it's a if you guys remember, the way we're solving that problem is like very so basically DP DPJ DPI, okay, DPI and J, okay. So I means the to paint the ice house and ending with color J, okay, and equals to what? Equals to the DP uh, I minus one, okay, and J JJ, okay, right? So what's this JJ means? JJ means one to from 1 to m, okay, from 1 to m, as long as okay, so we're gonna do a sum here. We sum this, right? From dpi minus 1 to jj, as long as the when I is not does not equal to jj. Okay, so what this one tells us is like the for get to the current state I and j. The j means the color, I means the house. Okay, color and house. What's the possible way to get to the current state? Right, that's from the I minus one house. As long as that color is not the same as j, we can just summarize everything from the previous state as long as this j is not the same as jj, because we are not allowed two consecutive colors basically. But for this problem, we're adding one more complexity here. You can think of that. You can think of that problem with this one here. Okay, if you make this row max all ones here, then this problem will be converted to this problem here. That will be a lot easier. But since for this one, we have this row max. Okay, that's add this one more layer of complexity. So what do we do for this? It's more like a generalized version of this one, right? For this one, it's always one, basically. The consecutive colors for each color is always one. That's why we can use this like simplified version of the state transition function. How about what happens when we have like this control here, this kind of like a row max here? We simply just need to add one more dimension of our DP state, I, J, and K. Okay. So what does this mean? It means that at the current I, right? At the current I, ice row, right? The I is the number of dice here. How many times we have died this we have rolled the dice. So I means the uh the n here, and j means the color. J means the color, and k means what's the consecutive times of this color. Okay, you can think of at the length maybe, or a count or something like that. Basically, for this color, what's the current length for this color? Okay, so with this one now we just need to think about how can we, I mean, how can we write our state transition function here? Okay, so let's think about this. So when k is greater than 1, okay, if k is greater than 1, okay, so what does it mean? It means that we can only get to this state from what? So basically the dp, this thing will I, j, k will equals to what? We can only get to the current state from the I minus 1, j, and k minus 1. Okay, so that if k is greater than 1, this is the only we can only get to the current I, j, and k from this one state, right? Because let's say the j is 6, okay? Let's say the j is 6 and the k is 3, which means at the current state we have we have we have a 6, and we already have like 3 consecutive 6. Okay, so what does that mean? It means that the previous state must be 6 and 2. Okay, because we can only get to 6 3 from 6 2. Right, so that's the easy parts. It means that we're rolling the same, we're rolling the the same numbers here. Okay, and yeah, and how about else? Okay, else what? Else basically it means to get to the current to get to the dp I, j, and 1, right? So else is the 1 here. So for I, j, and 1, because this is greater than 1, now we have all it's left is the 1. So to get to 1, how can we get the 1 here? Maybe you want to think about this is the tricky part. I mean, to get to length 1, we just need to loop through everything. Let's say from dp I minus 1 jj and kk, right? Because to get to the current state 1, the length 1 from the j here, we can basically we can loop through everything uh, from all the possible case and all the possible j's as long as the j is not equal to jj. Why is that? So because let's say if the j is equal to jj, then it means that the previous state is also j, and so this one cannot be get. This has to be like 2, 3, or 4. We only get 1 if the previously number is different as the current one, right? So basically that's our state transition function, and the range of the j is kind of obvious, right? The j is from 1 to 6, right? J is always from uh 1 to 6, and the k, what's the range of k? So the range of k will be coming from based on the current j, the range will be from will be the value of the row max here. That's the maximum k we can get. Okay, because basically that's all the states, all the possible k values we can get, and yeah, in here, right? So because here we will for the current dpi j and 1 here, we'll be looping through all the j's here. Basically it's 1 to 6, but how about the k here? The kk means the all the possible all the possible k's within this range here. Okay. Yeah, I think so. With those being said, I think we can try to code these things up. So like I said, we need a 3-dimensional DP array here, okay? And the initial state is always 0, okay? So, and yeah, so what's the case range, right? The case range, yeah, so the case is like within 1 to 15. So we can have like a 16 here, right? Just to be safe. And yeah, for each numbers we have this, and for in range 6, we can get a 6 here, okay? We can get a 6, and then we have another layer here for in range n here, right? That's how we define the 3 dimension here. Well, actually, you know what? Actually, I think we can compress our DP arrays from 3-dimensional to 2-dimensionals. We can just like maybe remove this one dimension because we will only be needing from the previously state, which is n minus 1. But I'm going to keep all the 3 dimensionals here just to make our state transition clear. Okay, so now let's try to write our main structure here, which is the loop here, right? So we loop from to the outer the most outer loop is obviously the n here, right? That's how many times we need to roll the dice here. And the second loop will be the numbers, okay? Yeah, we're using 6 here because even though we're 6 means 1 to 6, but we are using 0 to 5 to represent the 1 to 6 numbers. And because in that case, we can also use the j as an index, right, to help us find the max consecutive rows of this number. Okay, and okay, so that's that. And like I said, since we have three dimensions, so we need to add one more layer here, basically for k, right? For k in range, k is one based to gonna be row max j, right? So that's the most yeah, basically that's the most consecutive numbers this j number j can roll. Okay, and the 1 to this plus 1. Okay, and yeah, and now we just need to add our copy our state transition function here. Like I said, if k is greater than 1. Okay, so this is the this is the easiest case. Basically, the dp I j and k equals to dp I minus 1 j and k minus 1. Okay, so it means that if k is greater than 1, it means that we're rolling the same, we got the same number as the previous row, which means the j is the same, but the k and I has to be decreased by 1. Okay, else what? Else means else k is 1 equals to 1. Okay, so in this case, uh, mm, what we need to do is we have to basically loop through all the possible j and k's, as long as the j is not the jj is not the same as j. Okay, and what options do we have here? Let me think here. Because at this moment, let's say we have a k equals to 2. Well, actually, here I think there are two ways you can do the for loop here. So here we're using the k is greater than 1, and or k is equal to 1. Another way is we can just do another for loop of the number 6 here, 0 to 1 to 6, and we use that one to serve as a previous number. Okay, basically we use that, we check if the current number and previous number are the same. If they're the same, then the basically is equivalent to this k is greater than 1. If they are not, then it is equivalent to the k equals to 1 here. So okay, anyway, I'll try to finish this solution here. Basically, and if the k is equal to 1, so what do? We have to loop through all all the previously state. Okay, all the previous state, as long as the j is not the same as the current, the number is not the same as the current j, and for all the case, basically we're gonna have like for jj in range 6, okay, and the inner loop is gonna be for kk, okay, in range 1 to row max jj plus 1, because we are trying to get all the possible values for this jj here, okay, and if j is the same as jj, we simply continue, right? Because we know we cannot get to the k equals to 1 state. Else we do what? Else the dp I j and k, okay, equals to the dp I minus 1 jj and kk, because we have already limited the k to satisfy this condition here, okay? Yeah, so that's that. And I think we have to, since we're doing it like this I minus 1 j, yeah, so since we're doing the I minus 1 here, from we cannot do a n here. We cannot do 0 to n minus 1. We have to do or we can either do a like n plus 1, or you know what, I would or we can start from 1 here. But if we start from 1, we have to initialize 0 in this case. So what does 0 mean? 0 means at the first row, if we roll the dice only once, what's the value for those numbers? Basically, for I in for j, okay, for j in range 6, right? So that it means that we're doing the DPI here, right? So at the first time for these numbers, and the length will be 1, is 1, right? Because if we only roll the dice once, so for each number, the length 1 is equal to 1. That's the only one way to get to the current state, right? And okay, so after this one is done, all the values are saved into this three-dimensional DP here, okay? And all we need to do is we just need to summarize that, okay? I'm going to do a like simple summarize here. For j in range 6, okay? And then for k in range 1 to row max j plus 1. Remember, don't forget this plus 1 here. Answer plus dp. That's going to be n minus 1, right? Since this is the n minus 1 means we have already rolled n times, and j and k. Okay, return the answer. Don't forget we need to do a mod here. Okay, 9 plus 7. Okay. Yeah, I think this should just work. Let's try to run the code. Okay, so the test case passed. Let's try to submit it. Submit. Yeah, so I mean it works. So it's not the fastest one, but you know, so again, the time complexity, what's the time complexity for this one? N times 6 times 15. Another, yeah, another 6 and 15. Yeah, that's the time complexity here. Since we have like 1, 2, 3, 4, 5, we have 5 for loop here. How about space? Space is going to be the n times 6 times 15. Okay. Um, yeah, I mean, this problem, I know it's kind of tricky, especially for this part. Basically, I think the key idea of this problem is that you have to, so the k equals to 1, that's the special case. This is easy to think about if the k is greater than 1, but when the k is 1, basically we need to summarize summarize all the possible j and k's from the previous state. Okay, as long as the j and is not the same as the previous state. Yeah, I think, yeah, as long as you can figure out this part, I think the rest will be just some standard DP here. And this is the three-dimensional DPs here. So the first one is to enumerate the number of rows here. Second one is the current, basically this j, right? This j means the current number. And from here onward, basically we're doing something like, basically from the current numbers, right? We have to compare with the previous number. And the way we're doing here is we enumerate uh, this k here first. Actually, you know, we can try to enumerate the j instead of k to enumerate the previous number, and then we use the previous numbers, uh, the row max from the previous number to get to the current state. But I think that if we loop through the case here, it's also like a good way of finishing our solution, because it's aligned. The first three loop is aligned with our definition of the of our DP array here. So it's more, I think it's more intuitive. Basically, we fix all the loop here. We fix the current state, and then from here onward, we just need to figure out how can we get to the current state. Okay, so here again, right? So if the k is greater than 1, so there's only one way we can get to the current state, which is from the dp I-1, j, and k-1. But when the k is 1, we have to basically enumerate all the possible previously states, as long as the j is not equal to the previously number. Yeah, and then we summarize everything here. In the end, we simply summarize everything for this dp n-1. Yeah, I think cool. I think that's it for this problem. Uh yeah, if you I think one thing to take away from this problem is the um when you guys see this like consecutive constraints here, okay? And it means that you have to basically have another dimension of the state to remember the length of basically the length of the consecutive numbers. And then you have to and when you have like every time when you see consecutive times, you should always be remember the length 1 is the special case, because the length 1 means that you can get to the current state length 1 to any of the previously state. Yeah, I think that's the two things you might want to write down and review it once in a while. Yeah, and other than that, it's just like standard like DP template, like with this kind of constraints. And yeah, I think that's pretty much I want to talk about for this problem. And yeah, thank you so much for watching the videos, and stay tuned, guys. Bye bye.